In statistics, simple linear regression is the least squares estimator of a linear regression model with a single explanatory variable. In other words, simple linear regression fits a straight line through the set of endpoints in such a way that makes the sum of squared residuals of the model as small as possible. The adjective simple refers to the fact that the outcome variable is related to a single predictor. The slope of the fitted line is equal to the correlation between y and x corrected by the ratio of standard deviations of these variables. The intercept of the fitted line is such that it passes through the center of mass of the data points. Other regression methods besides the simple ordinary least squares also exist. In particular, when one wants to do regression by eye, one usually tends to draw a slightly steeper line, closer to the one produced by the total least squares method. This occurs because it is more natural for one's mind to consider the orthogonal distances from the observations to the regression line, rather than the vertical ones as old method does. Fitting the regression line. Suppose there are n data points, I equals 1, n. The function that describes x and y is. The goal is to find the equation of the straight line which would provide a best fit for the data points. Here the best will be understood as in the least squares approach, a line that minimizes the sum of squared residuals of the linear regression model. In other words, alpha and beta solve the following minimization problem by using either calculus, the geometry of inner product spaces, or simply expanding to get a quadratic expression in alpha and beta. It can be shown that the values of alpha and beta that minimize the objective function q are where Rxy is the sample correlation coefficient between x and y, and Sx and psi are the sample standard deviation of x and psi. A horizontal bar over a quantity indicates the average value of that quantity. For example, substituting the above expressions for an int yields this shows that Rxy is the slope of the regression line of the standardized data points. It is sometimes useful to calculate Rxy from the data independently using this equation. The coefficient of determination is equal to when the model is linear with a single independent variable. See sample correlation coefficient for additional details. Linear regression without the intercept term. Sometimes it is appropriate to force the regression line to pass through the origin, because x and y are assumed to be proportional. For the model without the intercept term, y equals beta x. The Ohl's estimator for beta simplifies to and the sample correlation coefficient becomes substituting in place of gives the regression through. The last form above demonstrates how moving the line away from the center of mass of the data points affects the slope. Numerical properties. The regression line goes through the center of mass point, if the model includes an intercept term. The sum of the residuals is 0 if the model includes an intercept term. The residuals and x values are uncorrelated, meaning model case properties. Description of the statistical properties of estimators from the simple linear regression estimates requires the use of a statistical model. The following is based on assuming the validity of a model under which the estimates are optimal. It is also possible to evaluate the properties under other assumptions, such as inhomogeneity, but this is discussed elsewhere. Unbiasedness. The estimators are unbiased. This requires that we interpret the estimators as random variables, and so we have to assume that, for each value of x, the corresponding value of y is generated as a mean response alpha plus beta x plus an additional random variable epsilon called the error term. This error term has to be equal to 0 on average, for each value of x. Under such interpretation, the least squares estimators will themselves be random variables, and they will unbiasedly estimate the true values, alpha and beta. Confidence intervals. The formulas given in the previous section allow one to calculate the point estimates of alpha and beta, that is, the coefficients of the regression line for the given set of data. However, those formulas don't tell us how precise the estimates are, i.e., how much the estimators vary from sample to sample for the specified sample size. confidence intervals were devised to give a plausible set of values the estimates might have if one repeated the experiment a very large number of times. The standard method of constructing confidence intervals for linear regression coefficients relies on the normality assumption, which is justified if either the errors in the regression are normally distributed, or the number of observations n is sufficiently large, in which case the estimator is approximately normally distributed. The latter case is justified by the central limit theorem. Normality assumption under the first assumption above, that of the normality of the error terms. The estimator of the slope coefficient will itself be normally distributed with mean beta and variance where sigma 2 is the variance of the error terms. At the same time, the sum of squared residuals q is distributed proportionally to chi2 with n-2 degrees of freedom, and independently from. This allows us to construct a t-statistic where is the standard error of the estimator. This t-statistic has a student's t-distribution with n-2 degrees of freedom. Using it we can construct a confidence interval for beta, at confidence level, where is the th quantile of the Tennessee-2 distribution. For example, if gamma equals 0.05 then the confidence level is 95%. Similarly, the confidence interval for the intercept coefficient alpha is given by at confidence level, where the confidence intervals for alpha and beta give us the general idea where these regression coefficients are most likely to be. For example, in the Okun's law regression shown at the beginning of the article, the point estimates are the 95% confidence intervals for these estimates. So in order to represent this information graphically, in the form of the confidence bands around the regression line, one has to proceed carefully and account for the joint distribution of the estimators. It can be shown that at confidence level the confidence band has hyperbolic form given by the equation asymptotic assumption. The alternative second assumption states that when the number of points in the dataset is large enough, the law of large numbers and the central limit theorem become applicable, and then the distribution of the estimators is approximately normal. Under this assumption, all formulas derived in the previous section remain valid, with the only exception that the quantile t*n-2 of students' t-distribution is replaced with the quantile q* of the standard normal distribution. Occasionally the fraction 1, n-2 is replaced with 1, n. When n is large, such a change does not alter the results appreciably. Numerical example. This example concerns the data set from the ordinary least squares article. This data set gives average masses for women as a function of their height in a sample of American women of age 30 to 39. Although the old article argues that it would be more appropriate to run a quadratic regression for this data, the simple linear regression model is applied here instead. There are n equals 15 points in this data set. Hand calculations would be started by finding the following 5 sums. These quantities would be used to calculate the estimates of the regression coefficients, and their standard errors. The 0.975 quantile of students' t-distribution with 13 degrees of freedom is t*13 equals 2.1604, and thus the 95% confidence intervals for alpha and beta of the product moment correlation coefficient might also be calculated. This example also demonstrates that sophisticated calculations will not overcome the use of badly prepared data. The heights were originally given in inches, and have been converted to the nearest centimeter. Since the conversion factor is 1 inch to 2.54 centimeters, this is not a correct conversion. The original inches can be recovered by round and then reconverted to metric. If this is done, the results become thus a seemingly small variation in the data has a real effect. Derivation of simple regression estimators. We look for and that minimize the sum of squared errors. To find a minimum, take partial derivatives with respect to and by multiplying both sides by we get before taking partial derivative with respect to. Substitute the previous result for. Now, take the derivative with respect to.